Okay, here we go with lesson 8.3. Like I mentioned in class, this is probably going to be the most difficult lesson in this chapter for some of you. And the reason for that is we're talking about proving things again, giving reasons. You may not have to do a full proof, but you definitely need to know the theorems and how to use them. So some of you may struggle with this a little bit, so make sure you pay attention, take good notes. This video may end up actually in two pieces where I kind of just tell you about the theorems, kind of show you how they work, and then maybe a second video where we just apply them to some pictures. All right, but let's start with a quick review of what we learned back in lesson 8.2. In lesson 8.2, we learned that if something was a parallelogram, then we had a couple different things. We had two sets of opposite parallel sides. And that came from the definition. All right? So two sets of opposite parallel sides. We also learned we had two sets of opposite congruent sides. And that was a theorem that we proved. We learned that we had two sets of opposite congruent angles. That was also a theorem that we proved. We learned that we had four sets of consecutive, or consecutive means right in a row, okay, consecutive supplementary angles. Supplementary adds to equal 180 degrees. And then finally, our last thing we learned about was that the diagonals bisect each other. Okay, so those were things that we learned. If something was a parallelogram, then these things had to be true. Today's lesson is basically the converse of a lot of those things. We haven't talked about converses in a while. Remember, a converse is where we switch the order. So instead of saying something like, if a quadrilateral is a parallelogram, then it has two sets of opposite congruent angle or sides. Okay, we're going to switch it around. We're going to say if a quadrilateral has two sets of opposite congruent sides, then it must be a parallelogram. All right, so that's basically what we're going to do. This one right here, the four sets of consecutive supplementary angles, is going to change just a little bit. And then there's actually one other one that doesn't completely relate to one of these. So keep in mind, this comes from the definition. So we're going to have a theorem that's basically the converse of this, a theorem that's basically the converse of this, a theorem that's basically the converse of this with a small change, a theorem that's the converse of this, and then one other one that doesn't quite apply exactly the same way as all of these. Okay, so let's take a look at these theorems. They do have numbers in the book. I'll go right through the same order as the book, and I don't want you memorizing them by number. If you put down, theorem 8.9 for a reason in your homework, I'm going to mark it wrong because I'm not going to go look up what it means. The only reason I'm giving you the numbers is so that you can match them with what's in your book. So we're going to start with theorem 8.7. All right, theorem 8.7 says if both pairs, okay, of opposite sides in a quadrilateral are congruent, then, I could spell congruent, it would help, then the quadrilateral is a parallelogram. Okay, so remember the if part of a theorem is our given. All right, the then part is what we're trying to prove. So we're going to take this if part, we're going to draw a little picture that has that as the given, and we're going to try to prove we have a parallelogram. All right, so let me draw a little picture here. We're going to talk about why this works. So I've got A, B, C, D. My if, my given, says that both sets of opposite sides are congruent, so I'm going to go ahead and mark that up. All right, we want to prove that this is a parallelogram. All right, so easiest way to do this, and for a lot of these proofs, this is going to be the easiest way to do this, is we are going to draw a diagonal. Now we know that this diagonal is congruent to itself by the reflexive property of congruence. So therefore this triangle is congruent to this triangle by side-side-side congruence postulates. And if these triangles are congruent by side-side-side congruence postulate, then this angle right here must be congruent to that angle right there by CP/CTC. All right, now, if we think about those angles, though, they kind of look like something else we've talked about. We've got a line here, we've got a line here, we've got a transversal here. They're on opposite sides of the transversal, so hopefully you guys are figuring out that these are alternate interior angles. If the alternate interior angles are congruent, then what do we know about the lines? We know the lines are parallel. So, and remember, that's using a converse theorem. That's why these, like I mentioned earlier, these things up here, they're basically converses. And we're going to use converse theorems as we do our proof. So alternate interior angle converse theorem tells me that BC is parallel to AD. Now that's not enough yet. So let's keep talking. We got these congruent triangles. We've got these congruent angles by CP/CTC. We've got these parallel lines now by alternate interior angle converse theorem. Well, let's continue. What about this angle here? Okay, in this triangle, it's between the side with 1 mark and 3 marks. It's across from the one with 2 marks. So over in this triangle, here's the 2 marks. Let's go across from it. It's between the 1 and the 3. So I'm going to go ahead and put 2 marks over here. Those angles are congruent also by CP/CTC. They're in the same position. Well, these angles, this is still a transversal, but they're touching these lines here, AB and CD. So they're alternate interior to AB and CD. And if the alternate interior angles are congruent, then the lines are parallel. So AB has to be parallel to CD. All right, so have we proved it's a parallelogram? Well, go back here again. Remember our very first one, 2 sets of opposite parallel sides? That was one of the things we learned about parallelograms. That came from the definition. And hopefully you remember, good definitions always work. Good definitions always work both ways. So if it is a parallelogram, then it has 2 sets of opposite parallel sides. If it's a quadrilateral, it's got to be 4-sided to begin with, and it has 2 sets of opposite parallel sides, then it's a parallelogram. Well, we just showed that this has 2 sets of opposite parallel sides, so therefore this must be a parallelogram. So we started with just opposite congruent sides. Okay, have to have a quadrilateral, but opposite congruent sides, here and here, here and here. We added in the diagonal with the reflexive property. We got side, side, side. We got CP/CTC for these angles, and then alternate interior angle converse theorem for these lines. And we did the same thing, another set of CP/CTC angles. Alternate interior angle converse theorem gave me these lines. By definition, this is now a parallelogram. So from now on, if you are told or you are shown a picture like the very original one where it's just the opposite sides being congruent, you don't have to reprove all this. You just say, hey, there's a theorem that says if both pairs of opposite sides in a quadrilateral are congruent, then the quadrilateral is a parallelogram. All right, so that's theorem 8.7. Let's look at theorem 8.8. Okay, kind of separate these things. Theorem 8.8 says, if both pairs of opposite angles in a quadrilateral are congruent, then the quadrilateral is a parallelogram. Alright, so go ahead and get that copied down if you need to. If both pairs of opposite angles in a quadrilateral are congruent, then the quadrilateral is a parallelogram. Alright, now let's draw this out. Alright, so we've got something that looks like this now. Here, here, We got this and this. We got this and this and this and this. Okay. Now, I'm going to do this proof a little bit different. Instead of getting parallel lines right away, we are eventually going to get parallel lines, right? But I'm going to start off by doing more of an algebra proof. Okay, so let's call this x. We don't really know what it is, but I'm going to call it x. Now, these are congruent. That was our given. So I'm going to call this x as well. And I'm going to call this y, and I'm going to call this y. All right, so we know that all four angles in a quadrilateral have to add to equal 360 degrees. So x plus y plus y equals 360 degrees. We know that 2x plus 2y equals 360 degrees. If we divide everything by 2, we get x plus y equals 180 degrees. This actually kind of looks familiar with something we did in a previous video. Okay, so we don't really know what x and y are. We just know that these two angles added together equal 180 degrees. Now, let's look at this. Let's say that I extend this out a little bit, and I extend this out a little bit, and I extend this out a little bit, and I extend this out a little bit. And we only look at that part right there, okay, right up over here. Notice how these are lines. We're not sure if they're parallel, but this thing right here is functioning as a transversal. These angles right here, hopefully you remember the correct term, those are consecutive interior angles. They're on the same side of the transversal, they're in between the lines we hope are going to be parallel, so they're consecutive interior angles. And we know that if the consecutive interior angles are supplementary, then the lines are parallel. So this line must be parallel to this line. Okay? That's the consecutive interior angle converse theorem. All right, now, what if we did it kind of going this way? So let's extend this out here. Let's extend this out here. I'm not even going to worry about this one because now I'm going to cover up the bottom here. Okay, once again, I've got two lines. I don't know if they're parallel yet, but this thing coming right through here now is functioning as a transversal for these two. All right, and these are in between the lines, same side of the transversal, they're below it, so they're consecutive interior angles, and it's still x and y. And we know x and y have to add to equal 180. So therefore these angles are supplementary, and therefore these lines are parallel by the consecutive interior angle converse theorem. Remember all these things we did before in one of our previous chapters. Okay, and they're now coming back to help us. Okay, so we just figured out that all the lines are parallel. Top and bottom are parallel, left and right are parallel. By definition of a parallelogram, this thing has to be a parallelogram. It's a four-sided figure with two sets of opposite parallel sides. So, if both pairs of opposite angles in a quadrilateral are congruent, then the quadrilateral is a parallelogram. Okay, so that's the second way you can do it. All right, got a couple more here. Let's go to Theorem 8.9. Now this one is the one that doesn't quite match up with any of these things. All right, remember I told you we basically have a converse of each of these? Well, this one is the definition. So good definitions always work both ways, forward and backwards. We just did the converse of this one. That was the first one. We just did the converse of this. Instead of saying if it is a parallelogram, then it has two sets of opposite congruent sides, we said if the quadrilateral has two sets of opposite congruent sides, then it is a parallelogram, so converse. We just did the converse of this one. Now we're going to kind of squeeze one in between here that doesn't quite match any of these, okay? So that's Theorem 8.9. So let's write this one down. Theorem 8.9. All right. If one pair of opposite sides in a quadrilateral are both, now the theorem in the book doesn't use the word both, but I think it's important that we say that. I'll talk later on why. Are both congruent and parallel. Then the quadrilateral is a parallelogram. Okay, so go ahead and get that copied down. I'm going to draw a little picture of it. I would like you to copy this picture down as well. Alright, so here we go. We've got a quadrilateral. We've got one set of sides that is parallel and congruent. Okay, so the shaded triangles mean parallel, the marks mean congruent. So what we want to do is we want to prove that this is a parallelogram. And once again, we're going to do that by either proving the opposite sides are parallel, both sets, we don't have that, or maybe we can prove both sets of opposite sides are congruent. We've already proven that if both sets of opposite sides are congruent, it's got to be a parallelogram. So we can kind of go about this a couple different ways. We're going to start off the same way we do a lot of these other ones, though. We're going to draw a diagonal. Let me get some letters here, W, X, Y, and Z. Okay, so I drew this diagonal. Now, we know that the diagonal is congruent to itself by the reflexive property of congruence. We know that parallel lines, we should start thinking about things like alternate interior angles, alternate exterior angles, and so on. In this case, we do have alternate interior angles. This is regular, this is not converse right now, because we already know the lines are parallel. We're talking about the angles. Now, look at the triangles. Do we have congruent triangles? Hopefully you're thinking about why we do. All right, look right here. What's this order? We got side, angle, side. Okay, look up here, it matches, side, angle, side. So we do have congruent triangles. Now, if we have congruent triangles, we can do a couple different things here. We could come up with some congruent angles here and right here, and those would be alternate interior angles then for these, and we could go converse and get parallel sides. Or we could say that these sides right here are congruent by CP/CTC. Let me put a third mark on there. I already have one with 2 marks. Third mark, all right? And we already proved, look back here, we already proved this. If both pairs of opposite sides in a quadrilateral are congruent, then it is a parallelogram. We already proved that. So right here, both pairs of opposite sides are now congruent. It must be a parallelogram. Okay, so we can even use that old theorem. All right, like I said, if you don't want to do that, you can do this. These angles are congruent by CP/CTC. This and this are alternate interior for these 2 lines here, which would make these lines parallel by alternate interior angle converse theorem. And once again then, we have a parallelogram by definition of a parallelogram. Okay, so a couple different ways we can get it here. All right, now let's go to our next theorem. Theorem 8.10. Theorem 8.10. So let's get that one right up here. We're almost done. We got Theorem 8.10 and then 8.11, and we're done with the theorems, and then we'll come back with another video and do some examples. I take that back. They don't seem to have Theorem 8.11. We'll have to look at that. It might be in the homework lesson part, but I'm definitely going to teach it to you anyways, even if they don't have it. All right, so sorry, just flipping through the pages of the book while I was looking at this. All right, here we go. If. Now, once again, the theorem in the book doesn't use the word both. I like the word both. I'll talk about why later. If both diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. All right, if both diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. So I'm going to go ahead and draw this out. I'll call it PQRS, and then I'm going to use an extra point T where the diagonals bisect. Well, yeah, do bisect, that was our given. Okay, so here's PQRS. You come down here with one diagonal, that was not very straight at all, sorry about that. Okay, another one here. We're going to call this point right here T. And we are told in the given that the diagonals are bisecting each other, so the diagonals are cutting each other in half. So this is congruent to this, and this is congruent to this. Now, hopefully you can figure this out pretty quick. Can I prove this top triangle PTQ is congruent to the bottom triangle RTS? Well, it's a pretty easy one if you remember some stuff we learned earlier in the year. We've got 2 sets of congruent sides. That's not enough. But we've got a really easy thing here. What do we got here? We got this angle and this angle, right? Vertical angle theorem. Side angle side. Top triangle congruent to the bottom triangle. And if the top triangle is congruent to the bottom triangle, then by CP/CTC, this side is congruent to this side. Okay, that's not quite enough. We could do this a couple different ways again. We could now go with maybe some CP/CTC here and here. Get some congruent angles. That's between 1 and 3. It's across from 2. This one over here is between 1 and 3, across from 2. Okay, so those would be the same spot. They're alternate interior angles. Alternate interior angle converse theorem would prove these lines are parallel. Hey, wait, we just did that. If one set of sides is both congruent and parallel, then the quadrilateral is a parallelogram. So that's one way to do it. Another way, what about this left triangle and this right triangle? I'm going to go ahead and do it that way. We got more vertical angles here. We've got this side. I don't feel like putting 4 marks, and as long as you put a mark that's unique, so I'm going to put like a V-shaped mark here, that's fine. Those sides are congruent by CP/CTC. Now we got side angle side again here. Side angle side, 2, 2, and 1, 2 marks, 2 marks, 1 mark. Over here, 2, 2, 1. So side angle side, these sides are congruent by CP/CTC. Goes back to our first theorem. If both pairs of opposite sides in a quadrilateral are congruent, and the quadrilateral is a parallelogram. So we got a couple different ways we can prove this is a parallelogram. It all started with bisecting the diagonals. Both diagonals bisect each other. All right, now the book does not have in the lesson itself Theorem 8.11. All right, so I thought they had it in the, maybe in the homework. I'm flipping through right now, and I am not, nope, they don't have it. So, but I'm going to teach this method to you. It is a theorem. It can be proven. So we'll just call it Theorem kind of 8 point extra or whatever. It doesn't have a number. It's not really in the book. I expect you to know it though. Theorem 8 point extra. How's that for a name? All right, last one. This is not in the book. Okay, if a quadrilateral has one angle that is supplementary to both of its consecutive angles, then the quadrilateral is a parallelogram. Alright, if a quadrilateral has one angle that is supplementary to both of its consecutive angles, then the quadrilateral is a parallelogram. Alright, I've got about 6 or 7 minutes to try to get this under 30 minutes. Alright, here we go. J, K, L, M. That's a really bad looking J, sorry. Alright, so angle J is supplementary to angle K. Angle J is supplementary to angle M. Okay, so those are my two givens. Alright, one angle is supplementary to that consecutive angle and to its other consecutive angle. Alright, so that is supplementary that way, and it's also supplementary that way. Okay, does that make sense? Now, these are actually congruent. All right, that's our congruent supplements theorem from a while ago. If two angles are supplementary to the same angle, they are congruent to each other. All right, but that's not going to come into play here. But that's why I can put the same marks there. All right, here we go. You notice if I kind of extended this out, extended this up and down, and extended this up and down, these two lines here, this would function as the transversal. These things are interior, same side of the transversal, so consecutive interior angles are supplementary, means I have parallel lines. So using these two, I get these parallel lines. Okay, now if I use these two, if I extend these two lines out this way, and we're at that JM function as the transversal, then these are on the same side of the transversal. They're over here on the right side of the transversal. They're between my parallel lines. All right, they're consecutive interior angles, and if the consecutive interior angles are congruent, then by the converse, the lines, in this case top and bottom, are parallel. Got some really bad triangles there. I'll try to shade them a little better here. Okay, so Definition of a parallelogram says this is a parallelogram. Okay, this is not in the book. It was in the older version of the book. I'm not sure why they didn't put it in the new version. Maybe because they realized that, yeah, you can use the consecutive interior angle converse theorem twice, and it's pretty easy to get it to be a parallelogram. But this shortens it up just a little bit, because remember, theorems are just shortcuts. All right, so there we go. Those are your theorems. That's how you're going to prove something is a parallelogram. Do a quick review of it, and I want to show you something. Okay, so I've got 8-7, 8-8, 8-9, and 8-10, and then this extra one. All right, now every single one, both quadrilateral, parallelogram. Okay, look at this one up here, both quadrilateral, parallelogram. Okay, let's look at this one here, both quadrilateral, parallelogram. Look at this one over here. Both quadrilateral, parallelogram. Let's look at this one here, the last one. Both quadrilateral, parallelogram. Now if you look at every single one of those, going back to the beginning, the quadrilateral part is at the beginning. You have to have a quadrilateral. Okay, the quadrilateral part here is at the beginning. It's in the if, the hypothesis part. Same thing, let's go here, right? It's in the beginning, it's in the if part. Okay, quadrilateral in the if part, our last one, quadrilateral in the if part. Both in the if part, every single one of these. Both, it's before the comma, both, it's in the if part. Both, where are we down here? In the if part. Okay, over here, both in the if part. The end talks about parallelogram. Parallelogram. Parallelogram, right? Parallelogram, parallelogram, parallelogram. So we'd never know it's a parallelogram to begin with. We have to know it's a quadrilateral to begin with. Then we have to know two things. That's where the both comes into play. There's got to be two things. Two sets of opposite congruent sides. Two sets of opposite congruent angles. One set of sides, but it's both congruent and parallel. So that's two things. I know I've got congruent sides and parallel sides. Now, in that one, this one can get confusing, so let me draw that one out real fast. It's got to be the same set of sides. If you have something like this, where you've got one set of sides that's parallel and the other set of sides that's congruent, this does not have to be a parallelogram. We're going to talk about this later on. Alright, but this does not have to be a parallelogram now. The way I have it slanted, it kind of looks like it is, but it doesn't have to be. So when you're talking one set of sides is both congruent and parallel, it's got to be that same set of sides. So this one doesn't necessarily work. Okay, so both diagonals bisect each other. Okay, so it's got to be both diagonals, not just one diagonal. We are going to have a shape later on where only one diagonal is bisected. And then finally, one angle is supplementary to both of its consecutive angles. So you need two things again. You need one set here and one set here. Now this is another one that some people get confused on. Let's say you have something like this. I'll even show it. You can have these be supplementary. And then you could also have these be supplementary. This is not a parallelogram. All right? You do have two sets of supplementary angles, but it doesn't follow the theorem. It says one angle is supplementary to two different angles, one in each direction, going here and going here. Here, this angle isn't going that way for supplementary. This angle is not necessarily going that way, and so on. So we don't have one angle working both directions, and that's the problem with something that looks like that. All right, so 5 ways to prove a quadrilateral is a parallelogram. We're going to do a second video. It'll be shorter. I'll give you some examples of how you apply these. All right.